So as we get into Module 4, we're going to break this into two different sections. The first section here will be Module 4.1. In this module here, we're going to take a look at torsion. Specifically, we're going to look at circular shafts and the angle of twist. Now, objectives within this chapter, this module here, we're going to relate back to our textbook to Chapter 3, specifically Section 3.1 and 3.2, where we look at 3.1 being circular shafts and torsion, and 3.2 being the angle of twist in the elastic range. Now, within this module, we'll cover a couple different topics here. We'll go through some key theories, key equations, look at it related to some applications, and then go through some problem solving. So as we begin Module 4 and Chapter 3 in our textbook, we'll take a look at a little bit of an introduction here. So we can see here, we're going to take a look at some structural members and machine parts that are in torsion, and they're going to be analyzed where the stresses and the strains in the members of the cross-sectional sections are subjected to these twisting couples or torques that we see here as T and T prime. So we come down to our diagram down below here, and we can see that we have, okay, an A and B over here, a couple different notations that represent these. So we can see in part A over here, we have these curved arrows right here in A. So you can see there, right there, we have the curved area, our T prime, and our T right there on either end of this member right here. So these are going to be our vector quantities. Now we can see we can also represent these by a couple vector that we can see over here in diagram B, where you can see we have arrow coming in here, and you have these small arrows going around this right here. So this is just two different ways that we can reference either with curved arrows or these couple vectors we can see in diagrams A and B. So one thing we gotta want to think about as we're looking at these different diagrams here and we're discussing torsion here is the directionality of all these arrows here. Whether we're using these curved arrows or we're using these couple vectors here, we want to pay attention to what direction they're rotating in and see how that relates back to whatever coordinate system we choose to use here. So one thing that's again going to be important that we've discussed a little bit before is our right-hand rule. So we want to make sure we understand, okay, if this part is rotating clockwise this way, how does it affect the next part? How does it affect the next thing it's connected to? How do we look at the interface between two different things? So as we continue on and these parts get more complicated, and it's not just one simple part like we see here in A and B in this diagram here, but this shaft is then connected to a motor or to a gearbox or to another shaft. We want to understand how they interact, what the directions of these torque vectors are, these curved arrows that we're showing here, and make sure we can relate that back with sign convention to our original coordinate system there, so we make sure we know what's positive and what's negative. So let's take a look at a slightly more practical application here. So rather than just the shaft we're looking at here, what we can see here is we have some torsional loads on these circular shafts, but these shafts are part of a larger system here. So we can see right here in diagram A, we can see we have shaft AB. So you can see right here, there's from A, there's to B right there. So you have shaft AB connected between. Now this is what's important here. What is it connecting? What is it physically doing? So this is connected between a generator over here at point B. So B is our generator point over there, and a turbine over here at point A. So we have to ask ourselves, okay, let's just think about this before we actually read the problem statement or what's going on there. How do we break this apart? What's really going on? How do these things interact with each other? So we can see the generator is going to turn on here, and it's going to turn the shaft in one direction here. And we can see, okay, it's rotating this way by that arrow right there. So that rotates that way. We have this turbine over here that's going to be resisting that rotation there. But then we also have these bolted interfaces here and here at A and B. So the shaft from A to B is bolted in and connected by those connections right there to the turbine and the generator. So now we think about that there and say, okay, well, at each of these interfaces at A and B, we're also going to have torques acting there. And it's going to be resisting it from one direction to the other. So that's where we just talked about understanding what direction things are rotating, which direction is being resisted, is going to help us draw these torque arrows, these curved arrows in the correct direction. This is important here, that we're saying whether it's clockwise or counterclockwise, is positive or negative, depending on your coordinate system. Physically drawing these curved arrows in lets us know which direction it is rotating. And it doesn't hurt down below to say, okay, counterclockwise is positive or whatever it may be for your system here. So then we move over and we take a look at our diagram B right here. So we say, okay, what's going on in diagram B? Well, let's break this apart. We'll break all these apart here. We know that this guy is rotating around this way, and then this guy is going to be opposing that direction of rotation there. So you can see these are opposite directions, T and T prime at interface B. And at A, we have the same thing. If it's still moving this direction, we have the torque going this way, and then it's resisting over here, our T prime right there. So again, now we have these 4 different circular arrows showing the torque vectors at B, which is at the generator and at the shaft, and also at A, which is at the shaft and the turbine. So A is at the shaft and the turbine, B is at the shaft and the generator there. Now we have these curved arrows letting us know the directionality of our torque right there. So these are important not only for the system as the whole to understand how it's rotating here, but breaking it down into individual sections, because when we solve these problems out, we don't want to solve the system as a whole right away. We want to take a look at, okay, let's just look right here at the generator. What's going on in the generator? Maybe it gives us some power requirements, things like that. We can figure out our RPMs after that. Or maybe it gives us an RPMs, we need to back out power. Or maybe we want to just see what's going on for internal stresses within the shaft here. So all that there, we still want to break these down individually and solve them separately. So this is important here, we see in diagram B, where we have these 4 different circular arrows. So let's continue on here and think about this as a problem. We'll continue on, we just discussed there, how do we break this down, look at the individual sections, this is a problem we're solving. So if this is a problem we're solving, we'd be given part A in the problem statement here. So part A tells us the generator provides a power at a constant revolution per minute to a turbine at shaft AB. So we talk about, okay, it starts at the generator, we can see what's going on, we already kind of stepped through the thought process behind this. But now let's think about this in terms of the actual stresses and strains in members of the circular cross section that are subjected to these twisting couples or these torques. So the way we need to think about it is actually starting back here at the turbine here. When we break it down, we create a free body diagram. So that's what B is, a free body diagram of shaft AB along with the driving and reactionary torques of the generator and the turbine respectively. So we have the free body diagram of the shaft, and then we have our reactionary torques or reactionary forces from our previous problems there for both the generator and the turbine as well. So the way we think about this is here, the turbine, if we come down here, is going to exert a torque T on the shaft. So that's what we see right here. Here's the T on the shaft exerted by the turbine there. Now the shaft is then going to transmit that torque to the generator. So there's the T right there on the generator right there, whereas the generator is going to create an equal and opposite torque, our T prime right there. So that's how we go from our problem, initial diagram in the problem statement, where we're told the generator provides a power at a constant revolution per minute to a turbine through some shaft. Well, from there, we want to break that down and create a free body diagram. So that's what we've done in part B here, is created that free body diagram looking at the torques and as well as our reactionary torques right there. So next we want to take a look at some internal stresses and how they affect our net torque. So how is the net torque due to these internal stresses? So what we can look at here is that the net of these internal shearing stresses is an internal torque. Now this is going to be equal and opposite to the applied torque, and that's important there, that this is equal and opposite. We can relate this back to equation 3.1 in our textbook here, and we'll spend a little bit more time and go into some details and applications and break down the variables for this in the next couple slides. Now, although the net torque due to the shearing stresses is known, what is not known is the distribution of these stresses here. So the distribution of these stresses is going to be what we call statically indeterminate. So if it's statically indeterminate, that means we must consider that there's going to be some shaft deformations. Now, unlike the normal stress due to axial loads, the distribution of shearing stress due to these torsional loads cannot be assumed to be uniform. So that's an assumption we made a lot before when we're talking about these axial loads and normal stresses. We can't make that same assumption now with shearing stresses and these torsional loads. So now let's go over here and take a look at this diagram. Up here on the top, we have a shaft that's subjected to torques at a section plane at C right there. So there's our section plane at C right there. So we're going to break this down and see what happens at C when we have these torques here. We have our T acting at A, and we have our T prime over here at B. So we break this down. Now we have parts A and parts B. So part A, we can take a look at right here. This is a free body diagram of the section B to C, which is this first section right here, with the torque at C represented by the representable contributions of small elements of area. These are small elements of area that we can see there, carrying forces dF at a radius r from the center section. So the section center right there. So you can see there's these DFs right there. These right there, what we're calling right here, these small elements of area. And you can see the DF at each one of those. So now we've broken this down in the free body diagram, distribute those loads for those internal small elements of area. Now part B down here is a free body diagram of section BC having all the small area elements summed up in a resulting torque. So what we've done is we've taken all of these small elements at all these areas, summed them all up, however many there are, and from that we have this equivalent torque right here. So a lot of times this is what we'll see. This is something when we're thinking about these free body diagrams, what information they give us, what information are we solving for here. We may want to get to the point where we have this this resulting torque over here at C. And when we have that resulting torque at C here, we want that represented by this right here, an arrow at C right there, rather than these individual elements right here. So these individual elements are something that we'll need to break down. So we look at these, and is it 2D, is it 3D? Either way, we need to break them down in terms of their components and figure out how they contribute to this total torque that we can put in here when we sum them all up for when we're looking at this free body diagram for section BC at this NC here. So let's zoom in a little bit closer and take a little bit more detailed look at what we discussed there. So again, this is the net torque due to these internal stresses right here. So we're considering the shaft AB for this entire shaft here. It's going to be subjected at A and B to equal and opposite. There's our equal and opposite right there, torques of T and T prime. So at A, we have this T right there. Here's our equal and opposite T prime over here at B like that. We take this section perpendicular to the axis of the shaft right here at C. So we can see that right there. We take this right here. For the section C, we cut this here at C, so now we have the section BC that we're looking at down here. Now we want to create these free body diagrams as we're going through and solving the problems here. So to maintain equilibrium of this portion BC of the shaft right here, there must be these forces DF on the cross section at C right here. So there's your C right there. Now we can zoom in a little bit better. We can see these forces right here, these small forces at each of those elements acting in certain directions there. So if this was 3D, it'd be X, Y, and Z components for this. They're all in plane though, because this is perpendicular to the shaft axis. So we can look at this as a 2D case and just say, okay, let's break these down in terms of X and Y components there. And we need to figure out how do these relate to a torque here that we see on the end of this right here at C. So all those individual elements, we can sum those up together to create a torque over here. And then on our simplified free body diagram right here, we can say, okay, this is now our free body diagram. If we take the section at C of this member, the section of the rod AB or shaft AB, and now we're just looking at BC right there. So how do we do that? We go back to that equation we discussed from our textbook right there, with the integral of rho dF is equal to T right here, where this rho is the perpendicular distance from DF to the axis of the shaft. So if we zoom in right here on our diagram in part A right there, we can see that is that distance. There's that perpendicular distance. So for each one of these DF elements, you can see that that rho right there is going to be perpendicular distance from DF to the axis of the shaft, which is right in the center of the shaft there. So now T, what is that? T is our torque. So recall right here, we have this relationship right here. Now dF is equal to tau dA. So this relationship here, where tau is the shearing stress right here on the elements of area dA. So dA is the area, tau is the shearing stress right there. So that can relate to our dF right there. So we can plug that back into that equation up here for our dF. So we can take this tau dA, plug in for dF there. And then we can say now we have the integral of this perpendicular distance right here times the internal shearing stress, the shearing stress right here, tau, times that area, dA, is equal to T, our torque right there. So that's how we're going to sum up all of those little dF areas right there based upon the shearing stress right there in order to get this torque right there that we're seeing at the end at C here. So next we want to take a look at the axial shear components here. So first off, let's take a look at this diagram over here to the left. We can see here we have our axis of the shaft right here. So this is running down like this. And what we have here is we have a small element in the shaft showing how the shear stress components act. So we come up here, this is the small element that we're concerned with, and now we can see we have right there our shear stress there. So let's think about this for a second. We have a torque applied to the shaft. This produces shearing stresses on the faces perpendicular to the axis. So if this is the axis here, this is perpendicular, and this is perpendicular right there. But conditions of equilibrium require that the existence of equal stresses on the faces of the two planes containing the axis of the shaft as well. So there we have these two faces right here, and those two right there as well. So now in order to demonstrate this here, we have the existence of this axial shear component. We're going to consider a shaft that's going to be made up of slats pinned at both ends of the disc. This is so we can get a good visual representation of what's going on within this. Now these slats are going to slide with respect to each other when equal and opposite torques, so there's your equal and opposite again, torques are applied to the ends of the shaft. So we can go down here, and now we're going to take a look at this diagram at the bottom. We have A and B, where A is undeformed and B is deformed. We're going to apply these torques, these equal and opposite torques, to the two ends of the shaft right here on both ends, and we can see that we apply this torque T here, we apply this T prime over here. Those are equal and opposite to each other, and now we can see with these elements right here, we draw these all out on those two different slats right there. We apply this torque here, and all of a sudden now we can see the existence of these axial shear components demonstrated in this diagram here, where we have these slats along the way, and see how it kind of deforms and moves with those slats. So this is now going to lead into this shaft deformation for our circular shafts right here. Now, we can take a look at our diagram up here on the left right here, and we can see we have this shaft is fixed to a wall. We have this fixed geometry right there as it's fixed off over side here. We can see it has some length right here going from A to B. The length is L right there. And then we're going to apply a torque to this end down here at point A and see how it deforms. Now, from an observation standpoint right here, this is what we're calling an angle of twist of the shaft is going to be proportional to the applied torque and to the shaft length, which again, we have that shaft length L there. And we can see that this is right here. This phi is going to be proportional to the torque, and this phi is going to be proportional right here to the length right there. Now, when subjected to torsion, every cross-section of a circular shaft remains plane and undistorted. So this is every cross-section of the circular shaft is going to remain plane and undistorted. So it's twisting on the outside, but the inside, if we were to go through and actually slice this up, these cross-sections are still going to be circular and remain plane and not distorted at all. So in the cross sections for hollow or solid cylinder shaft remains plane and undistorted because of the circular shaft is considered to be asymmetric. So you're rotating around that axis of symmetry right there, and that's why you have no distortion going on. So now we can see here for cross sections for non-circular, non-axial symmetric shafts are distorted when you subject them to torsion. So you can see now, if you look at this here, down on the bottom right here, we can compare this between A and B, where A is comparison of deformations for circular and B is for a square or a non-circular shaft right here, one that's non-asymmetric right there. You rotate the torque here, and again, really like to do this. Just imagine you're actually getting on there and you're twisting that like that and just thinking about it. You can see that there is no deformation of those individual cross sections if you slice it up. But now if you were to look down here at B for this square one there and you twist it just as we see there, you can already see the distortion in this 3D image right here. Now if you go through and cut up those into individual sections, you can see that there is going to be distortion within each of those sections there. So something just to think about, the geometry of the shaft that you're dealing with is definitely going to affect the actual shaft deformations for even as individual sections as you're looking at those. So ask yourself, based upon the geometry, is this something that is axial symmetric or not? So next we want to take a look at here is our shearing strain. So we can see we have our diagram over to the left. Within this, we want to consider an interior section of this shaft. Now, as a torsional load is applied, an element on the interior cylinder is going to deform into a rhombus. So let's take a look at that over here. Well, in part A, we can see here's our shaft over here. It has some length, L right here. You can see there's our center axis at O. Our radius coming out here to the end. This is that length C right there when we're at the max on the surface right there. And we can see our phi here for our angle of twist. So in part B, this is the undeformed portion of the shaft with a radius P, a rho. So we have this radius rho right there is our radius rho going out here to some point A right there. So now we can see this element that we're talking about right here on the shaft right here. When it's undeformed, it's a square element right there. Now as we deform this, and this point right here at A rotates up to A prime at this angle of twist here of phi, and we can see there's our radius rho right there leading up to that same A prime, same distance to A prime right there as it rotates up. Now what we can see down here is our shearing strain right there, our gamma right there, and we can see now here is this element that's been deformed right here into a rhombus right there that we were talking about there. So this is a deformed portion of the shaft having the same angle of twist phi right here and strain on angles of twist per unit length right there. We can see by our gamma right there, or our shear strain right there on the element. So now, since both ends of this element remain planar, so again, this is a circular shaft right here, so all those cross sections are going to remain planar along the way, the shear strain is going to be equal to the angle of twist, our phi right there, according to the following relationship. And we can relate this back to equation 3.2 in our textbooks right there. And it follows that we have this relationship here, the L, the length right here, our total length of our shaft right there times our shear strain right there, our gamma right there, is equal to our rho, which is that radius coming out from our center right there. And we can see it right there as well, coming out from the center right there, times that angle of twist θ. Or we can rewrite that and solve for our shear strain there, saying that our shear strain is equal to our radius rho right there times our angle of twist divided by the length right there. And that gives us a definition for shear strain, a relationship there from equation 3.2 in our text. Now, thing to think about here is the shear strain is proportional to twist and radius there. So we can say that the max shear strain is equal to C times the angle of twist over L, where C is that distance right here, right there. So we can say that the shearing strain is maximum on the surface of the shaft where our rho is equal to C. So C is that distance for rho, that radius, the max when it's on the surface right there. Now the shearing strain in a circular shaft is 0 at the axis, at the center right here, of the shaft, and then it varies linearly with the distance away from the axis of the shaft, and we can see that down here and this right here. So right there varies linearly as we go up there, our distance away from the axis of the shaft right there. As we come out like this right here, we can see it starts at the center 0 and varies along the way, as you can see it going there on this bottom diagram C. So next we're going to take a look at stresses in the elastic range here. So if we're dealing with the elastic range, talking about the modulus of elasticity here, we're going to bring in Hooke's law again right here. So if we take that previous equation we just looked at and we multiply by our shear modulus right here, so we can now say, okay, we have our shear modulus right here, our G value right there from Hooke's law is equal to, times our gamma, is equal to our rho over C times, again, we multiplied through by our shear modulus G right there is equal to G times our shear max right there. So then what we can do is we can sub in from Hooke's law. We go back in the previous chapter, but we can see it again in equation 3.5 in this chapter of our textbook as well, where our tau is equal to that shear modulus G times our shear strain right there, gamma. So when we plug that in now to the equation above right there, we can rearrange and we can find that tau is equal to rho over C, where rho is that radius, C is that max distance all the way out to the top surface where our shear strain is max right there, times now our tau max right there. And this is related back to equation 3.6 in our textbook here. So in this here, that the shearing stress varies linearly with the distance rho from the axis of the shaft that we discussed earlier there. So if we're talking about this for a solid shaft right here, we can take a look over on the right into diagram A. So this is a distribution of the shearing stress in a torqued shaft right here. So you can see as we move out right here in the rho axis right here, we can see that varies linearly from 0 at the center right here all the way out to a max shear, tau max right there when we get to that C at the surface of our, in this case, a round solid shaft right there. So now next we want to do is recall that the sum of the moments of the elementary forces exerted on any cross section of the shaft, these must be equal to that magnitude T of the torque there. And we can reference back to equation 3.1 at the beginning of this chapter here for our equation relationship for torque right there. We have the torque is equal to the integral of rho times tau dA right there. We can plug into that from a relationship up here for 3.6 and see that torque is equal to tau max over C times the integral, when we pull that out front as a constant, of our rho squared dA. And then from there, we can get our relationship now, which we see in equation 3.8 in this section of the textbook right here, that T is equal to our tau max over C times J, where J is now our polar moment of inertia that we can plug into that relationship here. So the results are known as the elastic torsion formula. So the two of these here, which relate back to equation 3.9 and 3.10 in our textbook here. So we see that tau max from a relationship in equation 3.9 is equal to our Tc over that polar moment of inertia J right there, or T is equal to, our tau is equal to our temperature times that radius rho divided by that polar moment of inertia right there. So for the max, we have C. For our regular tau, we have rho. And again, the reason why we're having C in the max is because this is going to be max. So we come out here and take a look right here when that rho is equal to C. So we can see that case right there. We're at C right there. That's why this relationship in 3.9 is for our tau max. So now we're going to continue on looking at the stresses in the elastic range here. And what I've done is rewrote out these elastic torsion formulas, 3.9 and 3.10 from your textbook there. We have tau max is equal to our torque T times that distance C, the radial distance C, divided by J, where J is our polar moment of inertia, and tau from equation 310 right here is equal to our torque times rho now there, that radial distance rho there, not necessarily at C, divided by J, that same polar moment of inertia. We're going to recall our torque is the internal torque in that section. So now these equations derive for a shaft of uniform circular cross-section subjected to torques at its ends. However, they can be used for shaft of variable cross-section for a shaft where subjected to torques at locations other than at its end. So you can see right here, we have this variable cross-section shaft down here going from B to A, where the diameter from B to E is different from that from E to C, different from that from C to A right there. So this is a variable cross-section right there, but we can see it is subjected to torques at locations other than its ends, because you can see this torque TE and this torque TC right there. So then what we can do is we can obtain, if we do this section right here at S right there, cut that in half, look at just this half here from B to S right there, what we can do is draw out our free body diagram. So we can obtain this torque T, this internal torque right there on the end, T, by drawing out our free body diagram of the portion of the shaft located on just the one side right here. So we're dealing with this left side from B to S right there of the section. And then from there, we're writing out our sum of our torques. These are some of the torques applied, including this internal torque, and saying that these are equal to 0. Solving that out, saying, okay, what are all my torques? Summation of all these torques set it equal to 0. Therefore, we can back out if we knew our T sub B and our T sub E was given to us. We had another way to solve for them initially. Plug those in, do that summation of torques equal to 0. Then we can back out that internal torque T located at that cross section S. So the next topic I want to discuss here is torsional failure modes right here. So we can see two different types of failure modes right here to a shaft that's subjected to a torque right here. Now we can have a ductile failure and a brittle failure like this here. So a ductile failure, we take a look right here, we can see there's our T and our equal and opposite T prime down here, twisting in equal and opposite directions to each other right there. And we have a ductile failure right here. It's a very clean break right through that there. Whereas we're talking about a brittle failure over here in B, we can see we still have this T and it's equal and opposite T prime over here for the torque right there. When it's brittle, we can see it snaps along this distance right here, giving this kind of twisted shape to the break right there. So what this is saying now is that these ductile materials that we see in part A generally fail in shear, whereas these brittle materials are weaker in tension than they are in shear. So when subjected to a torsion, a ductile specimen breaks along the plane of maximum shear, i.e., a plane perpendicular to the axis shaft. So that's what we see right here, is right along that perpendicular to the axis shaft right there. So this is our axis shaft right there. That is right here, again, going to be perpendicular right to that axis shaft. Now, if we're talking about a brittle specimen right here, when this is subjected to torsion, it's going to break along the planes perpendicular to the direction in which the tension is the maximum right here, which is along 45 degrees to the shaft axis right there. So if we look at this here, we can see, well, if that's the shaft axis going right there, or right down the center of it, if I can draw a straight line, this right here is roughly at an angle of about 45 degrees, right? We would expect it to be for a brittle specimen. So this is more of a practical application to get a visual right here, the difference between the different material types when you're talking about this torsional failure modes. So now let's apply some of these key equations and topics to a sample problem here from chapter 3. So let's take a look here at sample problem 3.1 here. Now we can see we have a given diagram over here. We have this shaft over here that goes from A to D. Now there's three different sections within the shaft here, so we can see it tells us now here that shaft BC, the center section of the shaft right there, is hollow. And this has an inner and outer diameter given to us as 90 millimeters and 120 millimeters for the inner and outer respectively. Now they also tell us that shafts A, B, and C, D, so from here A to B, from here C to D, are solid and have the same diameter, and that diameter is given to us as D. So we can see that labeled right there and right there. Now we can also see from the given diagram we have the length of the shaft AB as 0.9 meters. We have the length of our shaft BC as 0.7 meters, and we have our length of CD given to us as 0.5 meters there. Now, we can also see that they tell us there's some applied torques right here. So at point A, we have a torque given to us as 6 kilonewtons per meter. At point B right here, we have a torque given to us as 14 kilonewton times meters. And then we have a torque here at C of 26 kilonewton meters. And then at D, we have a torque here of 6 kilonewton meters right there. Now, the thing to pay attention to is you can see A, B, and D are all moving counterclockwise, whereas C is going clockwise there. So pay attention to that when you're talking about sign convention. So with all that information there, we can now go down and say, okay, for the loading that we see here, they want us to determine two different things within this problem. So part A, what do they want us to find? They want us to find the minimum and the maximum, so still two things within part A here, shearing stress for shaft BC. So we're really only concerned with shaft BC for part A right there, but we want to get the minimum and the maximum shearing stress for that. Now for part B, they ask us to find the required diameter D, so there's that D right there and that D right there, for shafts A, B, and CD. So these two shafts on the end here now, if the allowable shearing stress in these shafts is given to us as 65 megapascals. So now we're going to back out that diameter D if we're given the shearing stress right there. So in part A, they give us the diameters and we need to calculate the shearing stress. Now in part B, the reverse of that for the two other parts of the shaft, they give us our shearing stress, the maximum allowable shearing stress, and we need to back out that diameter D. So now the next step, if you were doing this problem out by hand, you'd create that setup page we've seen in some of the previous lectures and modules there, write down all your given information, again, those four different things that you want. You want the variable name, you want the numerical value, you want the units, and you want to know how it relates back to your physical problem there. Create all that, list out everything they've asked you to solve for in both parts A and parts B with the variable names there, any assumptions you're making, and then you would begin the solution. So as we're beginning our solution, you've already created your setup page. We want to take a look at this problem again. So I redraw out my given diagram here, and I say, okay, here's all my applied torques. They all have the same units of kilonewton meters right there. I have one A, B, C, and D. I can see the direction of them by these arrows that are given in the problem statement there. I know their lengths are all given here. And I know I have a outer shaft diameter and an inner shaft diameter for this hollow shaft right here for BC, which is part A right there. So what I'm going to want to do is I'm going to want to do some sectioning. So in my solution, the first thing I want to do is cut sections through AB and BC in order to perform static equilibrium analysis to find these torque loadings. So from there, within my procedure here, my plan of attack for this here, the next thing I'm going to want to do is to apply the elastic torsion formulas. So we just saw those 3.9 and 3.10 in our textbook there, but we're going to use those to find the maximum and the minimum stresses on shaft BC. So that's part A of the problem. We want to do that for BC. So we're going to use equations 3.9 and 3.10, these elastic torsion formulas, to the section right here for BC. We see there's our green line right there for section BC. From there, given the allowable shearing stress and applied torque, what we're going to do is invert the elastic torsion formula to find the required diameter. So this is part B right here, where we're going to use the reverse of kind of what we're doing in part A right there in order to back out that required diameter. So now what we've done, we've re-looked at this, we've created that setup sheet with all of our givens, all of our finds, all the assumptions here, and now we have a plan of attack. So this is something we haven't really talked about. This is another good thing to add in and physically write it. We've talked about thinking it through as we're looking at the problem. Okay, what do I see? What am I going to do? This is a nice, neat, organized way to do that. Come up with your procedure for analysis, plan of attack, solution steps. That way you know, okay, I think I need to do this and this and this step. Then for the start part A, I need to do this, and for part B, I'm going to do that. So maybe write those down so it jogs your memory as you're getting, focused on just part A of the problem. You forget, wait, what was I going to do next? What was part B? So having a little bit of a plan of attack like this, or procedure for analysis, is a good idea so you can reference back as you're going through the different steps of the solution and make sure you're staying on track. So now we can step through those procedure for analysis there step by step. And the first thing we wanted to do, we said we wanted to cut these shafts at A, B, and BC into sections. Look at those sections right there in order to perform this static equilibrium analysis to find the torque loadings. So the thing we want to think about here is deal with each one of these separately. I know I've did it both on the same slide here so we can look at them next to each other, but in your solution, deal with one at a time. You don't have to do them both in parallel with each other. This is just to kind of show the difference between those two right here in our solution. So for this one here, I'd probably start with AB, go through, draw out my free body diagram for section of AB there. So again, we cut that right between AB there. We can draw out our free body diagram. Well, what's going on here? Well, we have this torque at A, which is given to us as 6 kilonewton meters right there. And we can see, okay, there's our center axis of rotation right there, X right there. We're going to have this internal torque here at that section, which we're going to call here our tau sub AB. So with this free body diagram for the section between A and B right there, that we cut that right there, what we then want to do is the second part of this where we perform the static equilibrium analysis. So we can do our summation of, in this case here, summation of moments. Right here will provide our torques. So let's sum our moments about the axis of rotation. That makes the most sense. That's what we're physically rotating about. Let's sum our moments about that. So summation of moments about x in equilibrium, this is static equilibrium analysis right here, is going to be equal to 0. So we have our general equation right here. Summation of moments about x is equal to 0 right here. Let's go back up to the free body diagram that's right above us and say, what are these moments right here? So we can do our right-hand rule. We can say x going to y. Okay, this torque right here is going to be positive. Our T sub A is going counterclockwise. According to our coordinate system where x is positive going this way, this is going to be a positive torque right there of 6 kilonewton meters, and this is going to be minus, now opposite direction going clockwise, this is a negative torque AB, and this is equal to 0. So what this says now, if we rearrange this, if 0 is equal to 6 minus TAB, well, we can solve for our T sub AB there. The torque at that section of AB is equal to 6 kilonewton meters right here. Now, this is also the same because these are the same on both ends right there. This is also the same for CD. If we don't believe that, do out a third free body diagram here. Do this for that last section down there between C and D. Prove it to yourself that this is going to be equal to each other. So in this case here, now we've solved for our torque at AB, and from that, our torque at CD. So the next thing that we want to do is for the section we cut at BC right here. So we take a look at BC right here, cut that there. Well, there's still AB before it. So this is great that we solved for AB first now, and now we can go on to our BC right here. So we can go through this here, and again, draw a free body diagram. Well, I have my counterclockwise rotation of 6 kilonewtons here. I have my T sub B here giving me the problem statement as 14 kilonewtons going counterclockwise. Then I'm going to have my torque at BC, which is going to be going clockwise, which is going to be the opposite direction for our right-hand rule right there. So we say the summation of moments in our x direction is equal to 0 from this guy here. Well, we have a positive 6 kilonewton meters and a positive 14 kilonewton meters right here, minus, this is negative, is going clockwise compared to counterclockwise, our torque at BC right there. This is all equal to 0. We can rearrange our only unknown right here, one equation, one unknown, our torque at BC right there. We do that. Torque at BC right here is equal to 20 kilonewton meters right there. And this is all from doing our static equilibrium analysis of the free body diagram for both these sections A, B, and BC. So now at this point in the problem, I really like to reference back to that setup page and make sure I understand exactly what it is they've asked me to solve for and that I'm staying on track. So we go back and we realize we're looking for finding the maximum and minimum shear stresses in shaft BC. So that's what they asked us to solve for in part A. So we're not there yet. What we're going to do is we're going to apply these elastic torsion formulas. So we go back to our procedure for analysis that we spoke of. Okay, our next step is to apply these elastic torsion formulas, equations 3.9 and 3.10 from our textbook, in order to find this maximum and minimum stresses on the shaft BC. Now we also have to recall now, shaft BC is hollow. So we have known values for shaft BC that we can plug into this right here. So we take a look at this here. We can apply our equations right now, 3.9 and 3.10, for a hollow shaft right here, where we have our C1 and our C2 right here, which is going to be our inside radius and our outside radius here for that hollow shaft. So again, recalling the problem statement, they gave it to us as diameters. We want radiuses here for our problem right here. So we now can convert those to our C1 and our C2 right there. So now we can go through and calculate this here. So we can say from equations 3.9 and 3.10 in our textbook for these elastic torsion formulas right here, we can say, okay, we're solving for our J. Our J right here, plug in our polar moment of inertia here, is equal to pi over 2 times our C2 to the fourth minus C1 to the fourth, which is equal to, when we plug in our known values right here for C2 and C1, pi over 2 times our C2 is 0.06 to the fourth minus 0.05 for our C1 right here to the fourth power right there. We can do that out, and now we can get a value for our polar moment of inertia right here. Our J is equal to 1.392 times 10 to the negative 6 meters to the fourth. Now, why that's important is because when we come down here to use these elastic torsion formulas and we want to find that maximum stress, our tau max on the shaft at BC, tau max right here is equal to, in this case here, when we're at T2 according to our graph right here, we're out at a value of C2 right there. So this is equal to, from that relationship, our torque at BC times our C2 value right there, all divided by J. So our torque at BC, which we've calculated in part 1 of the, or the first step of this problem right here on the previous slide, was 20 kilonewton meters right there. Our C2 off of our diagram over here is 60 millimeters. Convert that to meters. Double check your units for unit analysis right there. Divide now by our J term right there. Plug that in. do out your unit analysis, make sure you end up in the right units, which we do. We do out our math here, and we end up with our tau max right here, our maximum stress on shaft BC for that hollow shaft is at point C on the outside of that there, where we're equal to 86.2 in units of megapascals. Now, we could do a relationship here for our T-min. We can say now our T-min over our T-max is equal to our ratio right here of C1 over C2, because we can see T2 is our max, T1 is our min right there. So we can do this just as a ratio right here and say T-min over T-max equals C1 over C2. We can go through this and plug in our known values. Well, our T-max we just calculated is 86.2. Our C1 is 45 millimeters. Our C2 is 60 millimeters. Again, you could convert to meters if you're not convinced that these units are going to cancel out there. Do that. We can cross multiply, whatever you want to do in order to solve for this T-min value right here from that ratio between your C1 and your C2 and our known value for our T-max. So our T-min right here, when we look at this here now, is equal to 64.7 megapascals. So what did they ask us to solve for? The maximum minimum stress on shaft BC. So I clearly boxed that tau max. Tau min, tau max is 86.2 megapascals, tau min is 64.7 megapascals. So that is what they asked us to solve for in part A for this problem. So now that we've completed our solution to part A, we go back to our setup page and double check, was there anything else they asked us to solve for? And yes, there was. There was a part B there. We can see that in our problem statement. We can see that on our setup page, and we can also see that in the little procedure for analysis we wrote. There's one more step. So in this last step for part B, we want to find this required diameter. So given the allowable shearing stress and applied torque, then we're going to go ahead from there and invert that elastic torsion formula right there, which was 3.9 and 3.10 in our textbook, to find this required diameter they're asking us to solve for. So in order to start our solution for part B of the problem here, what I want to do is draw out my free body diagram of the shaft on portion AB. So I'm looking at just portion AB. I'll draw all my torques here. So I have a 6 kilonewton meter torque here at A, and the same equal and opposite over here at B. So I go to that general equation right now for my elastic torsion formula right here. I see that my tau max right here in general form is equal to TC over J, where I have a relationship for J here for this shaft right here, which is pi over 2 times C to the 4th right there. Now what I can see right here is I know that my tau max was given to me, and I need to back out a diameter out of this here. So I can put in this here, my tau max is 65, so 65 megapascals is equal to T times C. So T is given to me as my 6 kilonewton meter load right there. So I plug that in for C. That's where this comes from right here. Then I've got a C on the top right here and a C to the 4th on the bottom. So I can get rid of that C at the top right there, and I just end up with C to the 3rd on the bottom right here. So that's where I come up with this relationship here now, and I see that 65 megapascals is equal to 6 kilonewton meters divided by pi over 2 times C to the 3rd right there. Well, now what I want to do, I have one equation and one unknown. I want to back that C out of there. So I reverse that, solve this for C, rearrange. I find that C is equal to 38.9 times 10 to the 3rd meters right there. I say, well, how does C relate to my diameter? Because that's the required diameter right here. So I can say, well, diameter is equal to 2 times the radius. C is the radius that we're looking for right there. So D is equal to 2 times C. So I can take that and say 2 times C right there. When I multiply that there by 2 is equal to 77.8 millimeters for our units right there. So that is that required diameter for part B for the solution to this problem.